Okay, solving exponential equations. So part A is just review of exponents. So take a few minutes, do A, B, C, D. I will pause this because let's just walk through these a bit. When you multiply powers in A, when you multiply powers with the same base, you add the exponents. So x to the 3 plus 12 is x to the 15. Power to a power in B, we multiply the exponents. 3 times 6 is 18. I don't need to see all of this. You could go from there straight down to the answer. So just recognizing that this is a larger power than this, so the answer will be in the denominator. And how much larger? It is 1 larger, so it's just x to the 1 in the denominator. More formally, 5, when you're dividing powers with the same base, then you subtract the exponents. 3 minus 4 gives you -1, and to write that as a positive exponent, we move it to the denominator. And lastly, it's going to be 2 to the 4, x to the, well, let's do this, -3 times 4. Let's throw one more line. So that's 16, x to the -12, which will be 16 over x to the 12. Solving exponential equations. Okay, so that's this whole lesson is on solving exponential equations. Chessboard has 64 squares, which alternate between 2 different colors. A fable says that the inventor asked for grains of rice in payment for his work in inventing it. He asked for 1 grain of rice on the first square, 2 grains of rice on the second square, 4 on the third square, and so on until all 64 squares were covered. So it is thought that the king at the time was done that, said, well, it's going to be like 8 on the fourth square, and then 16, and then 32. So like, how much rice could this be? Well, let's find out. So represent this relation in the form y is equal to a times b to the x minus 1. Now, we're used to exponential equations that look like a times b to the x, and this has an x minus 1. But there's a reason for that. And that is because when we start this, we're going to start on the first square, right? On the first square. And x represents the square number, but we're going to need that exponent to be a 0, right? We want the first one. So usually we write it as y is equal to a times b to the x, but our starting value occurs when x is 0. In this case, we're starting on the first square. So our starting x value is 1. So we subtract 1 from the square number to say, well, how many times have we doubled this thing? And y represents the, so a is our initial value, so it's 1 grain of rice. What are we doing each time we're moving squares? So we go from 1 to 2 to 4, so we're doubling. Then the base of the exponent becomes a 2, and then x minus 1, and it's just an x minus 1. So in essence, then we simplify this. Just write it as 2 to the power of x minus 1. And the minus 1 is simply so that we can start on the first square. So on the first square, 1 minus 1 is 0, 2 to the 0 is 1. Determine graphically which square on the chessboard would correspond to 128 grains of rice. So we're going to write 128 is 2 to the power of x minus 1. That's what we want to solve. To do that graphically, we can graph 2 to the x minus 1. So y1 is 2 to the x minus 1. And the value we want to get, y2, is going to be 128. Okay? And then we go into the graph and we find out what the value of x is. So let's pull up our calculator. Turn it on. I'm just going to clear this. So second, mem, 7, left arrow, enter, and 2. So resets. Let's go to y equals. So we have 2 to the power of. So depending on your calculator, if you had to put in the upside down v, the caret, and you see the upside down v, then go bracket x minus 1. If your calculator looks like this and it's already up there, then you can just put x minus 1 right up here. Like that, only actually get the x. X minus 1. Okay, so if you have an older calculator, you're seeing the upside down V for the power, then just go bracket x minus 1. In y2, we're going to put 128. We want to have 128, and we want to find the x value. So if we're going to graph that, so let's think about it. We're going to go to a window. We'll start off with x min is 0. Let's go to 10. I don't know if 10 is going to work, but we can go to 10. And we'll go by ones. Y min, well, we know we're starting with 1 grain of rice, but we'll just make that 0. We know we want to get to 128. So let's go like 150. And we'll go by tens. Okay, so we'll try and fit into the window, right? We don't want to go 0 to 128 or 1 to 128. We want to see a little bit of space above. Okay, let's hit graph. So there's your exponential function. And then 128, there's 128. So we got a good window. And we want to find the intersection, right? So we go second, calc menu. Number 5 is intersect. We move to about the point of intersection. And then it's asking first curve, so we're just going to hit enter. Second curve, we're just going to hit enter. So by moving to the point of intersection, we just hit enter 3 times. It's asking for the first curve. Yep. It'll jump to the second curve. Yep. And a guess, and we're pretty close. And we see that x is equal to 8. Okay, so let's go back here. So graphically determine. So our x values, we said, let's go from 0 to 10 by ones. Our y values, 0 to 150 by tens. Our graph looked like this. That was y1. Okay, so y1 was 2 to the power of x minus 1. y2 was 128. There's y2. And then we go second calc intersect. Right, where we just write down we're finding the x coordinate of the intersection, right? And we get x is equal to 8. So which square? Well, x represents the square number on the chessboard, so it would be the 8th square. Okay, so we can just say the 8th square. 8th square. Okay, so first square had 1, second square had 2, then third was 4, fourth was 8, fifth was 16, the sixth would be 32, the seventh would be 64, and the eighth would be 128. Solve algebraically for the square on the chessboard that corresponds to 256. So algebraically, we're going to start with, well, we start with our formula, right? We got a formula. We've got 256 is equal to 2 to the power of x minus 1. What we want to do now, to solve algebraically, what we need is the same base. So we're going to go with a base of 2. So we got to figure out, is 256 a power of 2? And then which power of 2 is it? So you just go to your calculator and you start playing with some numbers. Right, so we quit out of here. So you say, well, what's 2 to the power of 10? Okay, 1024, that's too big. What's 2 to the power of 8? 256. Okay, so we're good. We found it. So what we write is 2 to the power of 8 is equal to 2 to the power of x minus 1. So to algebraically solve an exponential equation, we need to get the base the same, right? The base of the power. When the base of the power is the same, what we can then say is, well, if these guys are both 2, then these two things here must be equal to each other. 8 has to be equal to x minus 1. right? So when you've got the same base, you can then equate the exponents. You can make them equal to each other. And then we solve that and say, what do we say? So x is equal to how much? 9, right? We're going to add 1 to both sides. Okay, so that's an algebraic solution. How many grains of rice would be on the 64th square? Well, we got 4, right? Let's just figure this one out, right? So, you know, and this isn't how many grains the guy's going to get in total. This is just on that last square, how many grains of rice would there be? So 2 to the x minus 1. Remember, x is the square number, so y is equal to 2 to the power of 64 minus 1. Means y is equal to 2 to the power of 63. So y is equal to, so 2 to the power of 63 is 9.22 times 10 to the power of 18. 9.22. 9.22. Well, that's pretty big, right? Like, what's 10 to the power of 9? 10 to the power of 9 is a billion. So that's a billion billion. And it's actually 9.22 billion grains of rice. How much rice is a lot? How much does that weigh? A lot. Is there that much rice on Earth? I doubt it. Are there that many stars in the universe? Probably not. Okay. 9.22, right? So 10 to the 9th is a billion, 10 to the 12th is a trillion, 10 to the 15th would be, let's call it a quadrillion. So this would be a quintillion. 9.22 quintillion. So lots of rice. Good deal for the guy, not so good a deal for the kid. Part C, using exponential equations, solving algebraic. So we need this common base, right? In order to algebraically solve an exponential equation, we have to have a common base. So we're going to ask ourselves, can 128 be expressed as a power of 4? You kind of think, well, I got 4 and I got 60 and I got 64, so no, I'm not going to get 128. But 4 can be expressed as a power of what number? 2. And 128 is also a power of 2. So we're going to write everything with a common base, which is going to be 2. So 4 becomes 2 squared to the 3x minus 1. Now remember, if we're dealing with two terms, right? Two terms, a binomial. We've got 2 terms in the exponent. We want to put it in brackets so that we're going to remember when we do power to a power, we're going to remember we have to apply the distributive law and multiply it through. And 128, we need to figure out that it's 2 to the power of 7. So I don't expect you to necessarily know that, but just know that 128 is a power of 2, and then you can just play with your calculator and go, okay, is it 2 to the 5th? No. 2 to the 6th? No. 2 to the 7th? Yeah, okay, that's it. Right? So you just have to figure out what power of 2. We now expand this, right? We use our exponent law, so this uses distributive law. It will give us 6x minus 2 is 2 to the power of 7. As soon as the bases are the same, then we can make the exponents equal to each other. Right? So now we can basically kind of say, okay, we can drop the bases and just say that means that 6x minus 2 is equal to 7, which means that 6x is equal to 9, which means x is 9 over 6, but that reduces to 3 over 2. So x is 3 over 2. Okay, so everybody follow the steps. So we need a common base. So for us, most times it could be like 2, 3, 5, right? We need a common base. We then have to express all the numbers as a power of that base. So generally, if it's even, you're probably using 2 as the base, right? But not always. I mean, 6 could be the base. Maybe you have 36 or 216. So figure out what the common base is. Express everything as a power of that base. Simplify any of the expressions. Okay, it just goes back to the first day we did on the exponent laws and stuff. Simplify the expressions. When you have a 2 and then to some power, then what you do is you equate the powers. You equate the exponent. 6x minus 2 in this case is equal to 7. And then you just solve algebraically. If we wanted to check this, we could go into the calc. So we've got 4 to the 3x minus 1. Okay, let's turn that on. We'll clear that. So 4 to the power of, okay, so 3. Our x, so I'm just going to go bracket 3 divided by 2. So that's our x, right? 3 times x, just put it in bracket so it does that. Minus 1. Okay, and I hit enter, should be 128, right? And it is. All right, do another one. 5. Well, 625. Sounds like it's got to be a power of 5, right? I mean, 5 isn't a power, anything. 5 is just 5. So it's 625 a power of 5. Well, try it out. Yeah,
5 to the 4th.
5 to the 4th. Okay, try 5 to the power of 4. So just go 5 times 5, enter, you got 25, times 5, 125, times 5. So we say 5 to the x plus 1 is equal to 5 to the 4th. Okay. Once the bases are the same and the exponents have been simplified, okay, so here we had to simplify the exponent first to get that. Then we can make the exponents equal to each other. So that means that x plus 1 is 4. So x is equal to 3. 8 and 16. What's the common base for 8 and 16? Going to be 2, right? Usually it's 2, right? Like you see 9s and 27s, then it's usually 3. Generally with even numbers, not always, right? Because here it's got 6. So 8, what's 8 as a power of 2? Okay, so 8, so we're going to write the 8 as a power of 2. We're going to write 8 as 2 cubed. We got to write 16 as a power of 2. What is 16 as a power of 2? 2 to the 4th. Okay, we just put those in brackets, right? So I'm replacing the 8, there it is in brackets. Replacing the 16, there it is in brackets. Since the exponent is a binomial, it's 2x minus 1, I'm going to put it in brackets. Just to remind me to multiply the 4 into that set of brackets, right? To distribute it through. All right, what's 3 times 3x? 9x. What's 2 to the 4th to the 2x minus 1? 2 to the 8x minus 4. Okay, so watch out. Make sure you're using distributive law. Sometimes you may have a negative sign. Make sure you're distributing the negative through, that you're changing signs. Okay, bases are the same. What do I do with these guys? What's 9x equal to? 8x minus 4. What's x equal to? Subtract 8x from both sides, get x is equal to negative 4. Okay, so that's an algebraic solution. So we're using algebra in order to solve exponential equations algebraically. We need to get a common base. Once we have that common base and we've kind of simplified things, so all we have is the exponent, no expressions up top that have to be multiplied or added or anything. We simplify those. And we've got the common base, then we set the exponents the same. What's a common base for 6 and 216? 6. So what power of 6 is 216? 3. Okay. So basically, you're not necessarily going to know, but you know that 6 is 6, right? 6 isn't a power of anything. It's not like 2 squared or 3 anything, right? 6 is just 6. That implies 216 must be a power of 6. You just go 6 times 6, okay, 36. Times 6, 216. Okay, how many times? I did that 3 times. So that's 6 cubed. But the root of 216, so, is 216 to the 1/2. So 6 to the 3x is 6 cubed to the 1/2. So 6 to the 3x is 6 to the 3/2. So we need to simplify it down, right? So we have the base and an exponent, and then the base and an exponent. No expressions in the exponents, right? So if you're still doing power to a power, you have to do the power to a power, right? We've got to multiply. When we have this, we then set 3x equal to 3/2, which means that x is equal to what? So if 3 times something is 3 over 2, then something has to be 1 over 2, right? Whatever you can do, you just go 3/2 divided by 3. And you can do that on your calculator. Just go 3 divided by 2 divided by 3. And you should get 1/2. Very important, we got to do a step first. What's the first step in E? Get rid of the,
I don't know.
can't get rid of the brackets, but what can we do with the 5? Nope, you cannot multiply it. You will try. You will get everything wrong when you do that. So you can't multiply a number into a power unless the number and the power have the same base. You can't go 5 times 2 to the whatever is 10 to the whatever. That is not at all true, right? But instead, what can we do with the 5? Divide. Yeah, get rid of the 5. So the idea is, if I want to get powers with the same base, and I've got a base of 2, it's like, let's get rid of this 5. And we're going to do that by dividing. And what's 320 divided by 5? 64. Is 64 a power of 2? Well, it should be if this is going to solve. So 64 is 2 to the power of 6. Okay, if you don't know that, it's fine. Just sit there on your calculator and play around until you find that it is 6, 2 to the 6. Okay, no more expressions to evaluate here, right? Nothing like this, 3 to the 1/2, nothing like this. It's got to be expanded, which means we can set what equal to what?
3x plus 1 equals 6.
Yeah, so subtract 1 from both sides and divide by 3. And x is 5/3. Okay, if you want to check, you can plug 5/3 in so that you can go 5 times 2 to the power of 3 times 5/3 plus 1. Hit enter, you should get 320. Okay, one more. 9 and 243. What's the base going to be? What's the base? Is it 9? I mean, you can try and see if you can get 9 to some power is 243. What's the base? 3. So when you see 9s, think of 3 as a base, right? Or 27s, or 81s, or 243. And 243 is what power of 3? Yeah, so 1 over 3 to the 5th. So we don't have a base of 3 on the right-hand side, right? Because it's sitting in the wrong spot. So we need to move this from the denominator up to the numerator, and what will it become when we move it? Yeah, so it'll become 3 to the negative 5. And what will this power be here? So we can simplify both sides at the same time. So what's this guy going to become? Yeah, 4x plus 2. So watch out, 243 is a power of 3. It is 3 to the 5th, right? But what you got to look out for is it's not 3 to the 5th, right? It's 1 over 243, 1 over 3 to the 5th, and that would be 3 to the negative 5. Okay, we both have a base of 3. We can make exponents equal to each other. 4x plus 2 is negative 5. 4x is 7. So x is 7 divided by 4. Negative 7. So negative 7 divided by 4. I was going to verify it, right? That wasn't going to, you should let me. Verify it. Try it. See if it works. That wouldn't work. And I get flustered. Oh, it's not working. What have I done wrong? Well, let's try it. See, it disappeared. So what did we have? What did we have? It was 9 to the power of what? No, I turned this on. So 9 to the power of, what was it, 3x? 2, was it? What?
2x plus 1.
2x plus 1. 9 to the power, here's what I'm going to do. I'm going to x, what did we say x was? Negative 7 over 4, right? Negative 7 divided by 4, store in x. I'm just going to put that into x. So by the store key, I'm saying take negative 7 divided by 4, put it into x. And now I can go 9 to the power of, and I'll just use brackets here, 2x plus 1, okay, and hit enter. And the right side was 1 divided by 243, right? 1 divided by 243. So in theory, they should be the same. Okay. So if they're the same, which they are, then you have verified, right? That, yeah, that really is that. So you can do that on a test, but do it later. Like, don't sit there on the test and verify everything as you're doing it. Go back. You got time at the end, go back, and then you can put in the negative 7 over 4 and stuff, and you can do some verifications. Solving graphically, rounded to the nearest 10th. Well, we don't really need to do that one graphically, right? Because 8 is a power of 2. So we don't have to do it graphically, but we can do it graphically. So what do we got? 2 to the 9x, and we've got 8. So I'm going to go to y equals. I'm going to clear that. Go 2 to the power of 9x. And this guy is 8. Okay, so if we think about it, if x is 1, we'll have 2 to the power of 9, which is way bigger than 8. So we know that we don't need to go like negative 10 to 10. So if I set a window, I'm going to say, well, if I go from 0 to 1, I'm going to be going from 2 to the 9x. If x is 0, 2 to the 9 times 0 is 2 to the 0 is 1. And when x is 1, that would be 2 to the 9th, which is actually 512. And we just want it to be 8. So we'll go from 0 to 1. Maybe go with the scale of 0.5. And 0 to, let's go to 20. Oops, let's go from 0. Clear. 0 to 20. And we can go by ones. And we hit graph. So there's your characteristic exponential function is that it takes off and it starts growing and then it starts growing really fast, right? So with exponential functions, they kind of start slow, right? They just sort of hover down near the bottom and then they start to move upwards. And when they take off, they really take off. So second calc, number 5 is intersect. So we want to move to about the intersection point. Where am I? Too far. See, I can see my y values are like 40, and I want my y value to be 8. So there we go. and move to about the point of intersection, hit enter 3 times, we get 0.333. Go back here. So y1 was 2 to the 9x, y2 was 8. My x window was 0 to 1 by a half. My y window was 0 to 20 by 1. My graph looked like this, and the x value was, the nearest tenth, 0.3. Okay, it's really 1/3. It was 0.333. So as a fraction, it's just 1/3, but they just asked for the nearest tenth. So the 5 and the 800 definitely can't be. We could have done the 2 to the 9x and the 8. We could have done those. We could have done that one algebraically, right? Because 8 is equal to 2 cubed. But with the 5 and the 800, we cannot do it algebraically, right? We can't express 800 as the power of 5. So we have no choice. Now, we could try and think of some numbers, because we know that 5 cubed, we just figured that one out. 5 to the power of 3 will be 625. So if I put a 3 in there, but that'll be a 2, so I got to put maybe a 4 in there, but we got to go bigger. So let's go with a 5. So y1 will be 5 to the x minus 1. y2 will be 800. My x window, I just said, let's go 0 to 5. That'll be plenty. Okay, and if your window doesn't show you what you want to see, you just adjust your window, right? Like you try it out. If you can't figure out what to change your window to, look in the table. Go second function graph, you'll see the table of values, and you'll be able to see what kind of values you're looking at. And our y window, let's go from 0 to 1,000 by 100. Okay, so let's go try those out. Go to y equals. Okay, so I'm just going to clear. So 5 to the power of, I'm just going to throw this in brackets. So it would work on any calculator. If you see the upside down v, when you go to the power of, just go bracket x minus 1. It would be fine. y2, we want it to be 800, 800. Window, I said let's go from 0 to 5. We'll go by ones. Let's go from 0, let's go up to 1,000. And we'll go by 100s. Or 1,000. We'll go by 100s. Okay, so that's the window we're going to set for this graph. And we'll hit graph. There's your exponential function. Notice it's just kind of crawling along the bottom pretty slowly, but when it takes off, then it really jumps up. Okay, so what we're looking for is off the x, right? We got to go further on the x. So I'm going to change my window. So let's go to 7. See what happens. So that should work because we know that the line was coming across there. And second function calc, number 5 is intersect. Move to about the point of intersection. You can just hold it down. I have to kind of bounce around with it. Enter 3 times, and we get x is 5.15. 5.15. Oh, rounded to the nearest tenth would be 5.2. Okay, so let's just say that here. X is equal to 5.2. So there's y1, there's y2. Okay, I'm doing second function calc. Calc, you get the x value. That's 1,000. This is 7. Okay. I don't need you to get too detailed, but if you just label the ends of the grid, then that should be good enough. All right, 8 to the 2x plus 1 is 1/2 times 3 to the x plus 1. So y1 will be 8 to the 2x plus 1. y2 will be 1/2 times 3 to the x plus 1. Okay, so let's do that. Y equals. All right, what do we got? 8 to the 2x plus 1. So again, I'm putting that in brackets, even though it's up there. I don't really need brackets on this calculator, but it doesn't hurt to just sort of set it aside. Hey, that's my exponent, right? And then, what was the other guy? 1/2 times 3 to the x plus 1. So y2 was bracket 1 divided by 2, bracket 3 to the x plus 1. I can put brackets. I don't need them on this, but you can. Okay, and then hang on, I gotta jump down off of this line and go there. I'm just gonna hit graph. Let's just see what happens. The blue curve is my first. Okay, do we get the second curve at all? So we're not seeing the second curve at all. So what I'm going to do is go into the table and look for some, oh, there's the second curve. So if stuff's happening, it's happening way down here, right? So let's go into the table, let's go look. So remember, we want y1 to equal y2, right? So you're going to see y1 and y2. We want them to be the same. And here, like, this is like 5.5 or 8.5. Now this is like 8 billion, okay? So no, like that's, and this is 120, this is 8 billion, this is 364. Whatever we're looking for is happening further up there. Okay, so let's go somewhere between, let's say, -4 to 0. Let's go -4 to 1. So from -4 to +1 by 1s. And then we don't need to go to 1,000. Let's see what the values are here. Well, 512. So we can go like, and these are all positive, right? So exponential will always be positive. 0 to, so we can say 500. 100 is fine. Okay, so there's our exponential, 8 to the 2x plus 1. So you can see it's pretty flat, and then it takes off. And here comes the other one. Again, also pretty fast. Like it's almost right on top of it. So what I'm going to do, I'm going to set the y min. I'm going to go like -50, just so we can sort of see what's going on around. We know it can never go below, right? An exponential function is always greater than 0. But I kind of want to try and see if, it's kind of like just lying on top of it there. All right, so let's just kind of look around here. Second calc, so we want the intersect, and we'll just kind of move over to here and just say, can you find one over here? And yeah, it did, -0.547, so -0.5. Right, go back here. X is equal to -0.5. That's rounded to the nearest 10. Okay, what do we say? Our x's were like from 0 to 5 or 0 to 4 by 1s. Or no, -4. It was like -4 to something. Up to that. Matter of fact, if it's actually around here, let's just go in. Well, hang on. We'll do the winner. -4 to 1 and then -50 to 500. Okay, yeah, something like that. Actually, because we don't know, I'm going to box this in. I'm going to do a zoom box. So that's number 1. I'm going to say, it's somewhere over here. I don't know where exactly. So we're going to move out a little bit this way, and we'll go up. Up, up, up. I'm going to hit enter. And then I'm going to move down way too far. I move down and move back up again to there. And I'm going to extend my box out to the right till it goes out past where the blue line is climbing up. So we just want to see what, can we actually see a distinct crossing space between the two? Will our arm get tired and fall off before we can get this enough times? So there's blue line. You can see it's climbing a little bit. You can see a little more separation there. And there's red line. It's still really close. It's really hard to tell where that's happening. But they do kind of look like they're crossing around here. Okay. Oops. We want to go back here. Okay, so we have a value. Applications of exponential functions. So a of t is equal to a sub 0, or this is called a naught. And the naught is this naught. Naught is not, naught is not. This naught is what the British use. So you know how we play tic-tac-toe? They play noughts and crosses. So a naught in Britain is like an O. And for us, it's a 0. That's a 0. So it's called a sub 0 or a naught. And basically, it's just the starting. It's what we're starting with. So a naught is the initial amount of a substance or the initial population. A of t is the amount of substance or population that exists after some amount of time. Okay? So exponential growth can be used to model the growth of a city and its population. It can be used to measure growth of bacteria in a tray. If you have bacteria in a tray growing at some rate, then you can use this to figure out how many there are. So this is how many you start with. This is what you're going to end up with after this time. And then you've got B, the base, which is your rate of growth. Okay, that's how it's growing. So the value of a painting increases by 4% per year. The value of the painting after t years can be represented by the exponential function v is equal to v naught times 1.04 to the t, where v naught is the current value of the painting. So current value, future value, base of the exponential function, basically the rate of growth, and then the amount of time. If the current value of the painting is $50,000, state an exponential function to represent the value of the painting after t years. So the value after the time is the initial value times 1.04 to the power of t. So really all we're doing is looking at this and saying we know what it's worth at the beginning, which is 50,000. So we plug 50,000 in for the initial value. What would the value, calculate the value after 10 years? So V is 50,000, 1.04 to the 10. Rounded to the nearest $1,000. Okay, so let's get out of that, clear that. So 50, 1, 2, 3, bracket 1.04, bracket to the power of 10. Okay, so we just put that in our calculator. Again, if you've got an older calculator, you have to figure out how to, make it do things. It's going to look a little different than this. And we get $74,012. So rounded to the nearest $1,000, it would be $74,000. Okay, rounded to the nearest 1,000, right? So it's over 74,000. The answer could be 74,000 or 75,000. This was $74,012. So to the nearest 1,000, it would be $74,000. Calculate how many complete years it would take for the painting to at least double in value. Well, that's a value. It's at 50,000. If it doubles, what's it worth? 100,000. So we need to solve 100,000 is equal to 50,000 times 1.04 to the t. So we can enter that into our calculator just as it stands, or we could say, hey, both of these I can divide by 50,000. So we could just get 2 is equal to 1.04 to the t. Okay, we can't solve that algebraically, this unit. We will learn how to solve this algebraically, but right now we can do it graphically. So y1 will be 1.04 to the t, y2 will be 2. Okay, so y1, let's clear stuff out, clear. That's going to be 2. This is 1.04 to the power of x. We can't do so we know after 10 years it's worth $74,000. So let's go maybe for 20 years. So 20 years by 1. And I know it's 50,000 to begin with. I'm still going to start at 0. I'm going to go from 0 to 150,000. 150,000. And we'll do that by, and this number really doesn't matter. I'll say 25,000. So by going from 0 to 150,000, I'm going to put its initial value in about a third of the way up, and its final value is about 2/3 of the way up. So when we look at the screen, we'll have like a third blank at the bottom and a third blank at the top, and we'll have everything we want to see in the middle. Well, 20 didn't seem to do it. Okay, did I make that 150? 150. 20 years, 25,000. Yeah, this 1.04. Oh, it's 50,000 times 1.04. I forgot the initial. So 50,000 times 1.04. That'll be better. Not starting at 0 that one, or 1 and none. See, I wasn't lying. It goes from about 1/3 of the way up to about 2/3 of the way up. I was apparently lying about that one. So what did I want it to be? No, I wanted this to be 100,000. 100,000 or not? 10,000. All right, third time lucky. Boom, there we go. So if that didn't fit, if the intersection of those was off the window, then I would just have to extend the x value out a little bit further. Okay, if that wasn't working for you, then you can go look in the table to see what x value should I be going out to. But this worked out okay. So second calc, want the intersection. You can just hold yours down, right? I can't do it on the board. It's weird. And we got 17.7 or 17.67. Let's see. How many complete years? So 18 complete years. So 17 years wouldn't be enough, right? It was happening at 17.7. So it would be after 18 years. Notice it says to at least double in value. So after 17 years, it wouldn't quite be at 100,000. After 18 years, it would be over, but that's fine because it's complete years and it's got to at least double. I mean, it's got to be worth at least 100,000. Now, if we go back and look at the graph, you can see 17 years would be here. The red line is the $100,000 line. 17 years would be under that. Can I trace the line? I don't know how to use trace on this thing. I never trace it. But 17 years would be under 100,000. 18 would be over, but it would meet this criteria. So I got these wrong, didn't I? 50,000 1.04 to the T, X, and 100,000. Okay. Oh, I divided it. Oh, should have done that. Sure worked. But I was graphing 50,000, not 2. That's why that didn't work. Half-life. Get a half-life. So we talked about half-life, right, in radioactive elements. So the equation for half-life looks like this. A of T, the amount of substance that remains after T, that should be a T, years. A naught is the initial amount that we start with. H is the time period it takes for the substance or population to divide in half. Sometimes called the half-life. Okay? So basically, what we're doing is a modification here with this T over H. We're taking the amount of time something is happening and we're dividing it by the half-life to find out how many half-lives. How many times should I multiply the initial amount by a half? That's what T over H is going to become. How many times do we multiply by a half? So radioactive iodine can be used to determine if a person has a thyroid deficiency. A healthy thyroid gland will absorb all of the radioactivity according to the model A of it's a previously healthy thyroid. Now it's absorbing radiation. So how healthy is that? But let's assume that it's not harmful radiation. So a healthy thyroid will absorb according to this model. So 100, 1/2 to the T over 8.1, where this is the percentage that would be in the blood after T days. So you start with 100%, and then it starts decreasing each day, and you have a certain amount. So patients are given a capsule containing radioactive iodine to swallow. 6 hours later and 24 hours later, the amount of radioactivity is measured using a gamma probe. Sounds like more fun at every step, this thing. Take this radioactive pill and send the gamma probe. Use the model to determine to the nearest whole number the percentage of radioactive iodine in the blood of a healthy patient after 6 hours and after 24 hours. Okay, so after 6 hours, we basically have A of 6 is equal to 100, 1/2 to the power of 6 divided by 8.1. Okay, well, that's just a calculator thing. So 100 times 1/2 to the power of, and I'm going to put this in brackets, 6 divided by 8.1. Okay, so that should work on any calculator, new calculator, old calculator. The older calculators will have an upside down V next to the half, and the newer calculators will show the exponent pushed up into the top here, superscripted. So 59.84. Oh, nearest whole number. So 59.84, 60%. And A of 24, so it's the exact same, only 24 instead of 6. So I'm just going to pull this down, and you can do that a couple of ways. So I can just arrow up, hit enter, it'll bring that down. I can arrow back, so when I get to the 6, I put in a 2. I go second, delete, go to insert, because I want to change that to a 24. So it becomes 24 divided by 8.1. Hit enter, and we get 13%, right, to the nearest tenth. We'll go here, and that's equal to 13%. The patient missed the 24-hour appointment, and when the doctor finally took the measurement, he determined the patient had a healthy thyroid. If the percentage of radioactive iodine in the blood was measured at 84.3%, calculate the approximate number of hours which had elapsed since the patient was given the capsule to swallow. Wait a minute, that doesn't make sense because the percentage radioactive in the blood after, oh, that's days. Days. Doing the wrong stuff. So, good lesson. Watch out. These are the time is in days, but this was given as 6 hours. So 6 hours is 1/4 of a day, 0.25. So we got to redo that. And 24 hours is 1 day. So this will be 1 divided by 8.1. All right, let's go fix that. So the 6 should be a 0.25. So I'm going to bring that back down. Go over here. So instead of 6, we'll go 0.25. So it's 1/4 of a day, 6 hours. So that's 97.88, 98%. And then the other one should be 1 day. So I could just bring that down, and I'll change the 0.25 to change that to a 1. Delete, delete. And 92. So 98 and 92. 98%, 92%. Okay, so we want 84.3%. That's going to equal 100 times 1/2 to the x over 8.1. Now remember, this will be days, and then we're going to have to convert it to hours. So we can graph this. Y1 will be 100 times 1/2 to the x over 8.1. Y2 will be 84.3. So remember, we're going to get days. So we know that 1 day is 92%. So if we're going to go out a few days, okay, so we got 100, 1/2 to the x over 8.1. Okay, so clear that out. So 100, 1/2 to the power of x divided by 8.1. And the other one was 84.3. And we can clear that out. So window, what do we say? We'll try 5 days. And we'll go 0 to 100 because we're dealing with percent, and we'll go by tens. Scratch that. So notice this is going down. This is exponential decay. We're going Q2 to Q1, and we are decreasing. And there's the 84.3. This will give us days. Second calc, we're going to intersect. So that gives us 1.995 days. So 2 days, 48 hours. Okay, so x is 1.995. Call that 2 days. Okay, so 48 hours.